Hello! This is a lecture on continuity. It's really important for us to understand what makes a function what we call continuous. Okay? So, in order for a function f of x to be continuous at one point x is equal to c, some point in particular, we need three things, and that's what we call the continuity checklist. So each time we want to test a function for continuity at a point, we're going to go one by one through each of these and make sure that they're true. The first thing that needs to happen is the function must exist at the point. Okay, so that means if you take the value c that you have for x and put it into f of x, that number has to exist, like a real number. That's also the same thing as saying that the value c is inside the domain of f of x. The second thing that has to happen is that the limit as x tends toward the point c of f of x must also exist. So go back to the video lectures on limits if you don't really understand that. You'll need to look at each one-sided limit, make sure that they match, and therefore the limit will exist for that function. Okay? The third thing that has to happen is that the limit that you calculated in step 2 must be exactly equal to the function's value f of c that exists in step 1. Okay, so we're going to see a lot of examples of this, but before we go into concrete examples, it would be nice to have a couple facts about some of our more common functions. For example, every single polynomial, make sure you can recognize a polynomial, because the great thing about them is every polynomial is continuous for all x. Now here I've written aka continuous because some places may just refer to that function as continuous. Over here I've said continuous at a point. That means that this continuity checklist checks out at each and every point, at each point c. But if somebody just says that a function is continuous and they didn't tell you what point it was, it means that the function is continuous for all x. Okay? So if you recognize a polynomial, you'll know that it's continuous for all real values of x right away. Rational functions, which you remember is the ratio of two polynomial functions, are going to be continuous for all x where the denominator is not equal to 0. So if you look at the video lecture on the limits of rational functions, you see that when the denominator is not equal to 0, those are the good spots because you're just going to get a real number out of the function. When the denominator is equal to 0, a couple different things can happen, but the important thing is that on a rational function, when the denominator is equal to 0, no matter what happens, f of c does not exist. Okay, so you're going to have a failure of number 1 on the continuity checklist whenever you are dividing by 0 on a rational function. So that's why I say they're continuous for all x where the denominator is not equal to 0. Okay, and lastly, piecewise functions, which we've been discussing quite a bit, they must be checked for continuity at each of the breakpoints. So a piecewise function can be defined as one thing at one point, another thing at another point, and usually there's like some specific value of x where we stop defining it as one thing and then we start defining it as another thing, and that value of x must be checked for the entire continuity checklist to make sure that it's continuous at that point. Inside each region, you'll have to consider what the functional form definition is in each of the region. Sometimes it'll be a polynomial or rational function, and then you can go back to these to determine the continuity over each region. Okay, so let's go on to some concrete examples here, and I'll leave the continuity checklist up so we can go step by step through the checklist. Okay, so the question here will be, is the function continuous or is it not continuous? If it's not continuous, we will call it discontinuous. Okay, if it is discontinuous, I'd like to know at what points it is discontinuous. So let's start with our first function. Let's say f of x is equal to this function right here, x minus 2x plus 1. Okay? The question is, where is the function continuous? Is it continuous for all x? Is it only continuous for some x? And then, if so, where is it not continuous or discontinuous? It's a polynomial, right? Hopefully everybody has recognized the fact that this is a polynomial. F of x is a polynomial, and that's because The reason it's a polynomial is because it's a bunch of combinations of x to positive whole number powers. And even though we see some fractions in front, I did this purposefully to make sure you understand that these are just the multiplicative constants. So those can be a fraction. However, you cannot have a fraction in the exponent. You cannot have a negative number in the exponent. But if it looks like that, it's a polynomial. So therefore, f of x is continuous. And once again, if I just say continuous and I don't say continuous where or for what x, it's implied that it means for all x. Okay, so you might see it this way, or you may see it like this. F of x is continuous for all x. Okay, so let's go on to another example now. A little bit more difficult one. What if we have f of x is equal to the number 20 over x plus 4? Once again, the question is it continuous? If not, where does continuity break down? Where is it discontinuous? So this is a rational function. This is the ratio of two polynomials, constant on top, linear function on the bottom. And you'll know that for a rational function, it'll be continuous as long as we're not dividing by 0, right? So let's find out where we're going to divide by 0. And this may remind you of questions that I asked in the past about what is the domain of a function. If I ever give you a rational function and ask for the domain, when you divide by 0, those values of x are not in the domain, right? So we have a divide by 0 at x is equal to minus 4. And that means that f of minus 4 does not exist. So you can see the breakdown of step 1 on the continuity checklist here. F of minus 4 does not exist. So therefore, this function is not continuous. This function is discontinuous. I'd like a little more information. If it's not continuous, I would like you to say, where is it not continuous? For what values of x is it discontinuous? And the answer would be that f of x here is discontinuous at all the problem points, which is for this one just x is equal to minus 4. Okay? So that would be the proper conclusion for the rational function. Okay, now let's take a look at another rational function. Over here, we'll look at this one in a little more detail. Let's say we have the function x squared minus 1 divided by x plus 1. Okay, so once again, a rational function. The question again is it continuous? Or if not, where is it discontinuous? And right away, hopefully, you look over here and you say, well, I can't divide by 0. It will never be continuous for values of x at which I divide by 0. And so we can conclude right away, f of x is discontinuous at x is equal to minus 1. Okay, similar to the last problem, but now I want to delve a little deeper and ask you for a little bit of review. What is the limit as x tends toward the point minus 1 of this function? Okay, you should be able to answer this question from the videos on limits. So go ahead and pause the video and try to answer this one. Alright, so you may think it does not exist because we're dividing by 0. In the last case for x equals negative 4, the answer was that the limit would not exist. However, this is one of the ones where it's going to cancel out. Okay, so perhaps you took a graph of this, and when you're working with functions, it's always a great idea to have a picture or a graph of what you're looking at, just to confirm it. And if you did take a graph of this, you may have noticed that instead of seeing a vertical asymptote in this graph looks suspiciously like a line. There's no vertical asymptote to be seen in the graph, so that makes you think that maybe it actually exists at x is equal to minus 1. Okay, so let's investigate it a little bit further. So, do you remember what to do for a question like this? Well, whenever I take a limit, the very first thing I do is just plug and chug to kind of see what I would get. Okay, so the first thing I'm going to do is just plug in x is equal to minus 1, which is the limiting value right here. Let me see what I get there. I will get minus 1 squared, minus 1, so that's 0. Minus 1 plus 1, so that's 0. 0 over 0, I've got the indeterminate form, okay? So whenever you get the indeterminate form, remember, That's not determined. Does it exist? Does it not exist? I'm not really sure. It's yet to be determined. It's indeterminate. So I have to do further investigations, and the usual thing that you'll be learning to do is consider factoring. Okay, so that's a big hint. If you didn't get this one yet, try to compute this limit by factoring out the numerator and perhaps finding a common factor with the denominator and canceling it out. Okay, so hopefully you see this familiar difference of two squares. Factors out like this on the top, and then we've got this on the bottom. And so what happens is when we're taking this limit, remember, x is very, very close to -1, but it's not equal to -1. So because it's not equal to -1, it's not a 0 on the bottom. It's not a 0 here on the top. And as long as things are not a 0, then it's cool to cancel them out. Okay? So the reason I can cancel them out is because x is not strictly equal to the point -1. It's just very close. So in this limiting case, that function up there is looking very much like this function right here, x minus 1, and that's what you see on your graph. You see it's got a y-intercept of -1, it's got a slope of +1, and so when I consider this limit, I'm just going to plug in x is equal to -1 into x minus 1, and I'm going to get -2. Okay? So what is a real actual graph of this function right here? It's actually not exactly the function that you see on your graphing calculator. It's slightly different because technically x is equal to -1 is not in the domain. Okay? So keep in mind for this function right here, f of -1 still does not exist. But although we cannot technically plug in x equals -1, we can still plug in values for x that are very, very, very close to -1. And when we do that, you see the behavior of the function is very, very close to -2. So that's why the limit exists, because the function is acting like it's tending toward -2 when x is tending toward -1. That's the answer for the limit. Now let's go over the continuity checklist when we're comparing it with this exercise right here. Which part of the continuity checklist has broken down here for me to conclude that f of x is actually discontinuous at x equals -1? The limit exists. We just showed that the limit's equal to -2. However, the function itself does not exist. So this is the part that broke down. And because number 1 broke, number 3 can't even be checked because this is equal to what? This point doesn't exist, you see? So actually numbers 1 and 3 have both broken down for us to conclude that it's discontinuous at that point. However, if I ask you if this f of x was continuous at x equals 0 or x equals 17 or x equals -100, then the function would be continuous at all those points. It's only discontinuous at that one single point. Okay? Now, if somebody asks you whether this function is continuous or discontinuous and they don't give you any point, then you will say it's discontinuous, because if the continuity checklist ever breaks down at any single point, then the function is called discontinuous, and we can be more specific and say it's discontinuous at that point. That's where continuity breaks down. Okay, great. So let's go into one more example, an application in the world of business for business calculus. Okay, and this is going to be a piecewise defined function. And let's say that it's some sort of pricing. Maybe I'm selling apples, okay? And I've got the price of apples set on a sliding scale depending on how many apples you want to buy. Okay, so let's see, the price of apples where x is equal to the number of pounds of apples that you wish to buy, the total price, let's call it capital P of x, the total price, or sorry, little p of x. I will say the price for all your apples is going to be 1.55x if x is under 10. So if you buy less than 10 pounds, the price per pound is $1.55, and your total price will be $1.55 times how many pounds you're buying. Now if you're going to buy 10 pounds or more, I'll give you a little deal. If x is greater or equal to 10, then I will say that your price is going to be $12.50 plus 1.25x. Okay, so if you want to buy more than 10 pounds, then I'll say that your price is going to be $12.50, sorry, a little mistake here, times So I'm going to say that it's a flat rate of $12.50 for the first 10 pounds, and then I'm going to charge you $1.25 for each pound over $10. So that's why it has X minus 10 right there, and that's my rule if you want to buy 10 pounds or more. Okay, so the question is P of X continuous or is it discontinuous? And then a more applied question is this a fair pricing scheme? Okay. Just so you know, for quizzes and tests, you will need to understand the continuity checklist. It will not be given to you. So this is conceptual understanding that you'll need to know for the test. So now I'm going to erase it and go ahead and pause the video. Try to answer this question yourself and then we'll discuss it together. Okay, so what did you conclude? Is P of X continuous? No, it's not continuous, right? P of X is actually discontinuous, and specifically at what point did the pricing scheme become discontinuous? Check the breakpoints, right? That was my starting thing, is that if we have a piecewise function, we must always check the breakpoint. And what I mean by breakpoint, for here, the breakpoint is x is equal to 10, because that's the value at which I change my mind on how I'm going to define the function. Okay, so that's what I mean by the breakpoint here. So let's check, let's go down the continuity checklist and see how it breaks down. Okay, does P of 10 exist? What's P of 10? That's right, P of 10 would be under here, x is equal to 10. So you're going to plug it into this one right here, 1250 plus 1.25 times 0. 10 minus 10 is 0. So P of 10 actually does exist. It exists and it's equal to 1250. So that's not what was wrong with it. Let's ask number 2. What's the limit as x tends toward 10 of P of x? You should probably also calculate this limit very carefully just for practice. What's the answer for this limit? If you remember what I talked about in the limits of piecewise functions video, I told you that whenever we have a piecewise function and we have to find the limit at a breakpoint, we must consider first each of the separate one-sided limits. And if those limits match, that's going to be the answer. And if those limits, those one-sided limits, do not match each other, then the answer to that is does not exist. Okay? So if you didn't do that yet, go ahead and pause the video here and tell me what each one of these one-sided limits is equal to. Alright, so as for a review, let's go over how to calculate these one-sided limits. X is equal to 10 minus, that means limit from the left, x is less than 10. So I'm going to plug the number 10 into here because x is very, very close to 10, but it's less than it. Okay? So when I plug it in there, I get 1550. Now, when x is very, very close to 10, but it's greater than it, then I will plug in that x is equal to 10 here, and that's when I'm going to get 1250, and these two things are not equal. Therefore, the limit, the overall limit as x tends toward 10 of P of x, does not exist, and so that's where the continuity checklist breaks down. Okay, so that's how we conclude that it's discontinuous at x is equal to 10. However, if I asked you, is this function continuous at x is equal to 4? Yes, because it's just a polynomial. How about x is equal to 20? Yes, because this is just a polynomial. It's two polynomial, actually two linear pieces. But the place that it breaks down in continuity is at the breakpoint x is equal to 10. Now my second question is a more interpretive question for business applications. Does it seem fair to have this pricing scheme for my apples? I would say no. And this is where we're going to start talking about the graphs of continuity. It's not fair if your price is going to make us jump. All of a sudden, a strange jump. And here we have that if I buy just a little bit less than 10 pounds of apples, the price is going to be very close to $15.50. But if I just buy a little bit more than 10 pounds of apples, or if I exactly buy 10 pounds of apples, the price will be $12.50. So it actually turns out that it's cheaper to buy 11 pounds of apples than it is to buy 10 pounds of apples, and that's not fair. That just doesn't seem right on either end. So that's the one where I'm going to say no for this as well. Now let's challenge you a little bit further. I would like to challenge you guys, let's pretend that you're the Apple salesman. How could you change your function p of x so that now it would be fair? Basically make the function continuous. So how could we change p of x, and there's multiple answers for this, to make the pricing fair? There's multiple answers, but I would like to invite you to try it out and just see what kind of answer you can come up with. What kind of change did you make to p of x here? There's a couple things that I could have done, but one thing I noticed was if I bought 10 pounds of apples exactly, I put the 10 in here, and this part would be 0, right? So what about changing this number right here? That would be an easy change that would then make it fair. If I change this number right here to match what would get spit out of this when x is equal to 10, then they would line up perfectly when x was equal to 10. So maybe I want to make this change the 1250 to 1550. Okay, so if I made the change here, took away this 1250 and made it a 1550, notice that that was the limit as x approached 10 from the left direction. And then you came up with 1550 there. So then when x is equal to 10, it would also be equal to 1550. Then the limit would exist. Then the limit would match the function value at the point, and then it would be continuous. That's one way to make it fair, okay? You can kind of think up some other ways to make it fair as well, and you can go ahead and play with that as much as you like. Alright, so before I close this video, let's just go over what it looks like to be continuous in a picture sense. Okay, so let's draw a nice big picture, and then I'm going to ask you, where is this function continuous and where is it discontinuous? And if it's discontinuous, what part of the continuity checklist has broken down? Okay. Okay, let's see. 3, 2, 1, minus 1, minus 2. Minus 3. Okay, so here's a function. I'll call this function f of x, and let's say it's got some height values like this, and this could be -1 there, and that could be 1 right there. Now we'll ask you, over the domain that's shown here, so let's say from x is equal to -3 to x is equal to maybe 5, let's say. So let's put a domain on here. The domain is x is inside -3 to 5. So x is between -3 and 5. Over this domain, where is the function continuous? Is it continuous over that whole domain? Is it continuous just for a few points inside it? If it's not continuous, at what point does the continuity break down, and which one of the checklists was violated there? Okay? So let's write it like this. Where is f of x discontinuous? I purposefully put some points of discontinuity on there, so I know there's some answers, but I want you to fill it out right now. Say x is equal to which values, and then, furthermore, y. And for the y column, you can put just the number of the continuity checklist that broke. Okay, was it number 1, number 2, number 3? And these are the x values at which it's discontinuous. Okay, let's have you guys try this out. So pause the video and try this out. Alright, so I'm going to just start over here on the left with -3, and I'm going to walk along it and see if I can tell visually where I would say it's not continuous. -3 looks just fine. All these numbers look just fine. When I get to -2 here, I see a corner. Did you say that this was a point of discontinuity? I hope not, because this is actually a point of continuity. Everything's just fine at this point. For example, does f of -2 exist? Yeah, f of -2 is equal to 2. Does the limit as x tends toward -2 exist? Sure, if I come at it from the left, I'm headed toward -2. If I come at it from the right, I'm headed toward -2. And does the limit equal the function value? Yes, they both equal the height of 2. Oh, sorry if I said minus 2, I meant the height goes to 2, okay? So everything is fine at this point, so this is actually a point of continuity, but I put the corner there, and I put another corner here, just to highlight a place that people sometimes get confused and might say it's discontinuous just because it looks like a corner. Okay, so those are points of continuity. Those are fine. Let's move right along here. And the next point I'd like to consider is this. This looks a little funky. X is equal to minus 1. What did you put for that? That's a point of discontinuity, right? So that's my first point of discontinuity. But why is it discontinuous? Going down the checklist, number 1 is, does the function exist at that point? Does f of minus 1 exist? Yes, it does actually, because I have a filled in circle right here. F of minus 1 is equal to minus 1. See, it's the height of minus 1 right there, so that's fine. Does the limit exist? Let's do a little bit of one-sided limits for review, and I want you to get these limits visually. So what is the limit as f of x as x tends toward minus 1 from the left, and what is the limit of f of x as x tends toward minus 1 from the right? Okay, let's see. When we're coming at it from the left, the height is tending toward 1. When we're coming at it from the right here, it's tending toward minus 1. So these are not equal. Okay, so why? Number 2 on the continuity checklist, the overall limit does not exist. So number 2 is the one that breaks down. Okay, that's why I put the number 2 there. The overall limit does not exist. Okay, moving right along, how about the point x equals 0? How about all these points when it's a flat line like this? Is that okay? Yeah, that's totally fine. That's actually a very simple polynomial, what we call the constant polynomial. So it's just equal to minus 1 that whole time. So that's all totally fine. Next point of interest right here, looks like there's a hole at 2. So that's going to be a point of discontinuity. So hopefully the next point that you pointed out was x is equal to minus 2. And for y, which number on the continuity checklist is the thing that broke down here? Does the limit exist? Yeah, the limit actually does exist. It's fine because as we tend toward 2 from the left here, the height goes to minus 1. As we tend toward 2 from the right here, the height goes to minus 1. So here, the limit, I'll just write this down for a review of limits, as x tends toward 2, overall of f of x is equal to the height minus 1. So it's not number 2 that broke. What about number 1? Does f of 2 exist? Not at all. There's no filled in dot here, okay? So f of 2 here does not exist because I haven't even drawn it in. So the answer is why? Because number 1 breaks down, f of 2 just plain old does not exist. All right, let me change this one a little bit to see if, to answer the rest of the question, looks like everything else is fine, right? So I didn't even, hopefully that didn't throw you off. I didn't even need that other point. The rest of the question is fine. But let me change the question just a little bit, just to push you a little further. What if I had a hole here, but then I put a filled in dot right there? Okay? Because now, number 1 would actually be okay. So I'm changing the problem, reconsidering it. Here, I said it was number 1 because f of 2 did not exist. But what if I made f of 2 exist by putting the dot right there? What if f of 2 now is actually just equal to the height of 1? See, I made it exist. So that exists. The limit is fine because the limit is just what it was before. As I tend toward the number 2, the height tends toward minus 1. But I would claim that x is equal to 2 is still a point of discontinuity. Can you guys see why that is true? Because of number 3, right? So in this case, if I change the problem to make f of 2 is equal to 1, the limit's value, which is minus 1, does not equal the function's value, which is 1. And that's a breakdown of number 3, that both of those things have to match. Okay, so those are all the different ways in which we can break continuity or cause discontinuity. And one kind of like rule of thumb is if you can draw f of x without taking your pen off the page, then it's continuous. That's just a little rule of thumb. If you do have a picture, or if you have a function and you want to take that function and graph it and draw a picture, then keep in mind that if you can draw the function without taking your pen off the page, then it's continuous. Now let's just look at this function and see how that's true. See, if I start over here, I can just draw this function, I can just copy it. Even though I'm at a corner, I can still keep drawing it without taking my pen off the page. However, right here, if I want to keep drawing it, I have to get my pen off the page. So that means that's a point of discontinuity. Can't be continuous if you have to take your pen off. Then I can just draw this flat line, that's totally fine. But when I get to here, if I want to fill this in, I have to take my pen off the page. Even if I didn't have this point, in order for me to say this is a circle, an open circle here, I kind of have to, well, yeah, some people would say, oh, I can draw that without taking my pen off the page. But you know what I mean. This open circle here causes it to be discontinuous. Okay, and then for the rest of it, you can just copy, copy, copy. And even though there's a corner, it's actually okay. You can draw it without taking your pen off the page. So that's a way for you to visually confirm continuity.